In this video, we're going to be converting decimal numbers into their floating point representatives. Floating point numbers are used by most modern or all modern CPUs to represent and store numbers, so it's very important to understand how a processor will turn a number from decimal into this floating point binary system. Before moving on with this, there are two videos that you need to watch in order to understand the full process. The first video is how to turn decimal numbers into their binary values. The second video that you need to watch is how to turn fractional decimal numbers into their binary values. I have videos on each of these topics on this channel already, so make sure you've watched these or you will get lost in this process. So let's take a look at a floating point number. We are going to use the number negative 0.625 as our first example. This is a decimal number in base 10. This is a negative fractional number. This is how it would be stored if it looked like a floating point represented number. This number in base 2 is the floating point representation of negative 0.625. So now we can take a look at how we get from this number to this value. Let's take a look. The first thing we need to understand is that a floating point number has three very specific parts. We have the sign, we have the exponent, and we have the mantissa. Now we're going to start converting our number from decimal into this floating point system. Before we start working on this, there are two things you should write down before you even get started. The first thing you need to write is your binary table for binary conversion. The second thing we need to write might not make much sense at the moment, but it's good to get it onto the page while it's in your head, because if you try and remember this in the middle of the problem, you might forget it. Write down that our bias is 127, and as long as we're working with a singular floating point number, this will always be the same. Remember that the bias is 127. We'll come back to this later, but it's good to get it onto the page while we're thinking about it. So now we're going to colour coordinate our number in order to be able to work through this more effectively. So the first thing we need to know is what our sign is. The sign of a number is simply the representative of if the number is positive or negative. Because our number is negative, our sign is -1 to the power of 1. If our sign were positive, our sign would be 1 to the power of 1. So our sign is -1 to the power of 1, which, as we know, equals 1. That's already the first part of our floating point number calculated. Let's calculate the rest. The next course of action is to look at the rest of our number as two separate parts. First of all, we have to the left of the decimal point, and then we have to the right of the decimal point. We're now going to convert both of these into binary. So to the left of our decimal point is 0, because 0 in binary is 0. Next, we're going to need to look at our fractional part, and we need to convert this fraction into binary. .625 in binary is 101. So 0.101 in base 2 is equal to 0.625 in base 10. However, we need to keep going further with this. This number will now be represented as 0.101 times 2 to the power of 0. The next thing we need to do is move this decimal point. The decimal point must always have exactly a singular 1 to the left of it and nothing else. In order to move this decimal point into a location where it has a singular 1 to the left of it, we need to move it here. And we need to do so in the fewest possible hops. This is done in one hop, and because we're moving to the right, this number is negative. If we were to be hopping to the left, it would be positive. This leaves us with a new number. Let's write our new number out. 1.01. And this would be represented as times 2 in base 10 to the power of this number, so times 2 to the power of minus 1. We now have one final step left to complete to get to our final number. The first thing we need to do is work out our mantissa. Our mantissa is simply everything in the red section here, to the right of our decimal point in the original number. That would be 0, 1. The next step is to work out our exponent. Our exponent is the bias plus this value here from our exponent, so our bias plus minus 1 converted to base 2. So 127 is our bias as we previously discussed. So 127 plus minus 1 equals 126. Now let's convert that into binary. So 126 in binary equals 0, 1, 1, 1, 1, 1, 0. So now we have our mantissa, and we have our exponent, and we have our sign. Let's put that all together. Our sign is 1, our exponent is 0, 1, 1, 1, 1, 1, 0, and our mantissa is 0, 1. Our mantissa, once complete, will have trailing zeros for the remainder of the storage. Have you noticed yet? This number is exactly the same as the number we presented over here, which means 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, zeros is equal to negative 0.625 in base 10. Let's do a couple of more numbers to make sure you've got the grips with it. I've arbitrarily decided a second number for us to take a look at. This number will be 29.75. Let's begin our process. Again, the first thing we need to do is write down our binary table to ensure we don't forget it. And our bias. These two things are important to remember. Now let's begin turning 29.75 into its floating point version. So we have 29.75, and this number is positive. So first of all, our sign is 1 to the power of 1. Otherwise, we know that equals 0. Next, we need to work out 29 in binary, so let's do that. (29) in base 2 is 0, 0, 0, 1, 1, 1, 0, 1. Next, we need to work out 0.75 in binary, so let's do that. 0.75 in binary is 1, 1. And now we're going to represent this as times 2 to the power of 0. Now we are going to float our decimal points. Again, if we want a singular 1 to the left-hand side, we need the decimal point to be placed here. So let's hop it across. 1, 2, 3, 4. That's 4 hops, and because they're going to the left, those hops are positive. So now we can write our new number. First of all, we have 1.1101111. And now we can represent this as times 2 to the power of positive 4. Now we can start turning this into our final floating bit number. First of all, we can take our mantissa, which is 110111. Again, the mantissa is everything in this number to the right of the decimal point. And now we can work out our exponent. Again, our exponent will be our bias of 127 plus the number found here, which will equal 131. So now we need to work out 131 in binary. So if we put this number in here, 10000011, this leaves us with our final number of 0100000011, 110111, and then trailing zeros. And this number is our floating point representation of 29.75. And now I'm just going to do one final number to be sure that you understand it. The third number we're going to look at is negative 0.45. So again, the first thing we do, write down our binary table to be sure that we don't forget it. And we write down our bias. Again, to be sure that we don't forget it. And now let's begin the process of translating this number. Negative 0.45. We know that our sign is negative, which means that it is negative 1 to the power of 1, which we know is 1. Next we need to convert the left-hand side of our decimal point into binary, which we know is 0. And next we need to convert our fractional into binary. So let's begin doing that. Okay, so our fractional in binary is 0.1110011, and then this 0011 will repeat infinitely. Again, if you're not quite sure why this is the case, please ensure you have watched my video on converting fractional decimal numbers into binary, and then it will make more sense. And now we can represent this as times 2 to the power of 0. Next we need to start floating our decimal point. So, in order to get a singular 1 to the left-hand side of our decimal point, we have to move it to here, and that will be in 1, 2 hops. Because we're hopping to the right, this number is negative. Now we can write out our new number. Our new number is 1.110011, and again, this 0011 will repeat. And it will be represented as times 2 to the power of negative 2, because that's the amount of hops we have to do. And now let's start converting this into our final floating bit number. The first thing we need to do is get our mantissa, which is 110011, and the 0011 will repeat infinitely. Lastly, we need to get our exponent. Again, our exponent is our bias, 127, plus our exponent from here, which is negative 2. This equals 125. Now we need to work out 125 in binary. And now we can put this into our number here. And now we have our final floating bit number, 10111101, 1100110011001100 is our final floating bit representation of the number negative 0.45. Hopefully this has helped you work out how to turn numbers from decimal values into their floating point representations. If I can help any more, please let me know. Thank you for watching.